Hey, welcome everyone to Guillaume Bellegarda seminar. It's a pleasure to have Guillaume visiting the Department of Mathematical Sciences of Politecnico and to give seminar. Let me mention first that this seminar is organized within the IEEE-CSS Italy chapter initiative Road to CDC. The CDC Game Control Conference this year is in Milan in December, and there's this initiative of organizing this series of seminars, and there's also a Best Master Thesis Prize that you should be aware of. There are some leaflets here, and everyone is encouraged to apply. The 10 best master theses in the field within the last couple of years will get free entrance, free registration at the next CDC. Okay, that said, Guillaume is visiting us from EPFL, where he's a postdoc scholar. He got his PhD at the University of California, Santa Barbara. And before that, he got his undergrads at Berkeley. And today he's going to present his work on deep learning, optimal control, and bio-inspired control for dynamic robots. We are very happy to host you here. Please.
Thanks a lot, and very nice to be here. First time in Torino for me. So yeah, I'm from the US, and first I'll just apologize that there is a lack of theoretical results from the top title. So first, I just want to expand a little bit on my brief academic trajectory. So yeah, I'm a postdoc right now at EPFL for the last 3 years. So right now I'm working on deep reinforcement learning and bio-inspired circuits for quadruped locomotion. So this will be at the main part of the latter part of the talk. Of course, I did a 1-year postdoc at University of Southern California. So there I was working on also deep reinforcement learning, trajectory optimization, and FEC for dynamic motions, both for quadrupeds and also for vehicles. And then before that, I did my PhD at UC Santa Barbara, 2016 to 2019. I did that optimization for wheel-legged systems, also for vehicle drift parking. And so I'll talk about at the beginning. Before getting into more specifics, I'm going to talk about our general robotic system goals at the intersection of robustness, agility, and energetics in stochastic environments where there's variability. So what do we mean by robustness? We want our systems to do well, even under unknown variability. So for example, here we have A1 walking with an unknown load on top of the robot, or maybe here we have some uneven terrain over bumpy grass. So we don't have like direct knowledge of this. We don't want the robot to fall over. By agility, we mean we want to be able to do well in areas that we do know about, right? So maybe we have some kind of gap crossing task we want to do. We want to be able to plan some motions to cross as quickly as possible. If we know something about the environment, to be able to navigate around it, maybe something about the coefficient of friction, to be able to plan some dynamic parking maneuver. And ideally, we want both robustness and agility while being as energy efficient as possible. So wheels are very energy efficient, and we can still plan some dynamic parking maneuvers, for example, here. And of course, here there'll be some trade-off between each of these goals, right? So maybe we need to use a bit more energy to be more robust in the rough terrain. This is a good trade-off. So to accomplish these goals, there are kind of 2 popular approaches right now in robotics, right? On the left, we have more model-based control, where we have some system dynamics. We write down everything. We try and optimize for some particular goal, right? Maybe to jump and run over some particular emotion. This can work well if we have a good model of our dynamics and can read these fast enough, right? Here's the Docker robotics challenge. There's some model mismatch that is occurring between what we've planned and what's in the real world. So this is kind of one of our drawbacks here. Also, can we plan this fast enough? And on the right, we have more learning-based approaches. So through data, we're going to try and either collect a lot in simulation or see what we can get on the real world, and then try and see, okay, can we learn some control policy to kind of get this arbitrarily good performance that we see in literature. But there's also some drawbacks, right? So we train something with deep RL, we might get some strange control policies. So technically, this humanoid, for example, is moving forward robustly. It's not falling, but we're not going to be able to deploy this on the hardware. There's something like not good about it. We don't know what it's learned. There's no safety or anything. And so what I've been trying to do is how do we bridge the gap between both these areas? And the question that I'm trying to work towards is how can we build generalizable, agile, robust, and safe systems? So I'd first like to introduce the main topic of my PhD. So I was working on the JPL robot RoboSimian. So it's a dexterous quadruped with 4 limbs. Basically, there's 4 manipulator arms attached to this body. It's stable, but very slow. So the motors are very slow. The speeds peak at 1 rating per second. So the main topic of the PhD was, okay, how do we get the system to move more quickly? So one idea is to attach these passive single wheel skates to each of the forearms. It's just basically latched onto the arms. We'd like to be able to say, okay, how can we get the system to move more quickly by just reconfiguring internal degrees of freedom to get the system to skate forward. So now we have 6 degrees of freedom, and be able to set the 6 degree of freedom pose for each of the skates. However, since these are just basically velcroed onto the legs, there's no sensing the skate contact. We don't have any wheel encoders or anything like that. So first thing to do here, maybe to generate some skating motion, look at some have some assumptions about our wheels, and then do some kinematics, trying to get the system to move forward. So some important assumptions here is that they're passive, right? So we don't actuate the wheels, there's no motor at the wheel. There's no skid or slip, so based on the distance each wheel rolls, it's exactly equal to the radius times the wheel angle. We can rotate about some point contact with the ground, so it's just free rotation by the contact, and there's no slip. The wheel is moving forward. So now if we reason about some internal degrees of freedom, the kinematics, so y here is the distance between the base and outwards, the lateral direction from the skate, and then phi is each of the skate angles. We can make some offsets right between like forward, front, and rear wheels. We're trying to minimize the time that all wheels are pointing in the same direction, because then we can't control anything there. And here we have some motion that we've generated to skate forward. We can also plan omnidirectional agile trajectories, so skating on 3 limbs laterally, maybe around some point contact with the ground, around the base center, around one of the skates here. And this works well if we have high enough coefficient of friction on flat terrain. But what happens when the terrain's uneven? So here we have 4-limb skating on the left. So here's basically the tabletop at a restaurant problem. We're breaking and making contact with one of the wheels. So this is not robust. Right, we don't have flat terrain. With 3-limb skating, it's a little bit better, but ideally we want something a little more rigorous and general to be able to skate better. So let's try and see if we can do something with optimal control, but basically we just saw these non-slip constraints can be violated, right? The wheel will slip, we're going to make a great contact, so how can we improve this? One idea is to use a linear complementarity problem. So this is a very common model for breaking and making contact in robotics. So you're going to see, can we use the same thing to represent a wheel? So typically we'll have an isotropic friction model here with the wheel. We're going to say, okay, let's do an anisotropic friction model and actually just consider friction, the forces laterally with respect to the wheel rolling direction, and then see if this is enough to plan and optimize for movements. So with RoboSimian, we're also going to make some simplifications. We're not going to optimize over the full degrees of system. We have 7 joints in each of the limbs. So we're going to make some assumptions. We're going to have have all the mass of one leg at one of the skate contacts. So here we now have 4 contacts. We have the mass at the center of the robot. Each of these wheels are going to have this more simplified LCP wheel model. And we'll optimize over this and then try and do various tasks. So with this wheel model, for example, optimize for this dynamic parking maneuver. So for example, here, now we are optimizing through contact. You can see that this wheel is perpendicular to the rolling direction here. So it's basically skidding to be able to turn more quickly when we start it with some velocity. So this is the MATLAB animation, this same maneuver. Then we have Mujoko simulation of the skidding maneuver. So I didn't have access to the real systems. This is in simulation for this work. Also, by changing just the cost function, now we want to maximize the forward body position while minimizing energy use. Now, instead of this kind of constant kinematics with sinusoidal waves we had before, we were trying to do this by hand. And the optimization finds as we gather speed, where we can get smaller amplitudes to be able to move faster. So as we gather speed, we don't need to do such exaggerated motions. And this is the Joko simulation of the same maneuver. And now since we have legs, really the interesting thing here is can we do some hybrid rolling or walking and trotting? So in the optimization, we can also put, for example, a gait. So we have some context schedule that we're putting in. So static walking gait, we're bringing 1 foot at a time. Static trotting gait, we're bringing up diagonal limbs off the ground at the same time. So this is towards like if you want to come over some kind of partially rough terrain, maybe go over a curb. So this would be towards that kind of maneuver. And so, yeah, I didn't have access to the system afterwards. Actually, there's a GIF of the robot exploding from JPL if you look online. That's why I didn't have it. So we're also looking at seeing, can we do the same kind of, does this wheel model also apply for vehicles? So here we have a very short time horizon where we need to get to some parking location. So basically, it's impossible to get there without a fast acceleration, and then a skid in the short kind of time horizon. We have 2 examples here. We're going to skid forward and also some backward skidding maneuver using the same kind of wheel model. Now it's actuated, so we're actuating the forces in the forward direction for each of these. So this was nice, but we couldn't get it to work in real time yet with LCD wheel models. We're also looking if we can get inspiration from the vehicle dynamics community. So one popular model here is the dynamic bicycle model. And what we use here is we simplify the car system. So we have both the wheels of the front limb of the front axis, which is a bicycle, and same with the rear wheels. We're just trying to figure out, okay, what are the lateral forces at each of the wheels? And then one popular model for fitting a tire here is this check a tire model. It's also called a magic tire formula because it has really a physical meaning. But one thing about this tire model is that it would depend on the slip angle. And the slip angle is basically the angle between the wheel rolling direction. So here we have XW, and then the overall velocity of the wheel. So here the wheel would be skidding upwards. And so we get the slip angle alpha. So here it depends on the velocity, the x right of the wheel. And so this is in our denominator here for the slip angle. So if we put this into some optimal control, right, so we're doing some optimization. At low velocities, this is going to blow up. We're not going to be able to convert it numerically. So how can we try and get around this if we want to optimize over various velocities, maybe stopping the traffic, maybe also purely lateral drift. So one observation is that at low velocities, kinematic model actually is a good approximation, right? Maybe the forces are less important. We can define something like some short parking maneuvers problem. So maybe we can use the kinematic model at a lower velocity, and then higher velocities use the dynamic bicycle model where now the forces are more important. And here we're just going to basically interpolate between these models based on maybe some velocities that we have some pre-existing knowledge about of when they're important. And then here, this is going to be based on the overall velocity of the car, so both forward and lateral velocities. So what can we do with this model? So we're going to look at 3 different tasks. So first is steady state drifting, where we'd like to have some forward velocity and also some yaw rate at which we drift at. Also, we care about drift parking generation. So we'd like the car to end at some particular position and orientation at the end of some longer trajectory. And afterwards, we're going to track this trajectory basically online using nonlinear MPC on some shorter time horizon. What does this look like? So here we have some steady state drifting. We're using the nonlinear MPC with this fused model to do various donuts of different sizes. So here all we've changed is the cost function between these. So by changing the desired yaw rate, basically we can get smaller or larger sort of circles. And also it's important to note, so at the beginning, when it starts from rest, it's using the kinematic bicycle model region of the state space that quickly transitions as a dynamic bicycle model region of the state space as we gather speed. We can also plan for drift parking. So offline, we have some 2-second trajectory. We want the system to get to some particular location. If we just execute this feed forward, right, there's some dynamics mismatch, right, between this kind of simplified dynamic bicycle model and then the real dynamics of the system. But if we track this online with our nonlinear model of rate control, now we can do a lot better and get very close to the desired trajectory.
So the one on the right, okay, the one on the left is MATLAB simulation.
Animation, yeah.
Animation, yeah. The one on the right is,
This is the dynamic simulation in Gazebo OCE.
okay, so it's a simulator, but more with a more elaborate.
Yeah, so this is not a simulation, just animation with
Yeah,
what
it's
to
an
do.
animation, yeah.
This is the dynamic simulator.
Okay.
Yeah. And yeah, we're trying to put this on the car right now with some master's students and also trying to improve the model with some data. So next part, I'd like to move a little bit into reinforcement learning. So what I've been working on a bit more recently. So brief review, reinforcement learning as a Markov decision process. We have some agent that gets observation of the world, form of the state. Based on the state, it's going to choose some action through this neural network. This is applied to the environment, which we're going to now transition to a new state, possibly get some reward, and then basically we want the agent to optimize its expected return from how many rewards can it accumulate over some crimes. So typically for quadruped locomotion, we need to set up this Markov decision process based on the available sensory data that we have and what kind of motors and action we can take. So typically we'll have some IMU where we can get some body linear and angular velocities, maybe orientation from the base. We'll also have joint states, so what are our motor angles and velocities. And then if we try and solve this end to end, the action would be, okay, let's directly output, take all this information through the network, we're going to directly output motor position through torques. This is going to be applied to the environment, and then our reward function might be, okay, we'd like to move forward and be energy efficient, so we're going to penalize power, for example. So if we try and train this end to end, this is kind of a naive learning approach. We get some kind of strange behaviors with RoboSimian. It's almost on the brink of collision, right? It's not necessarily falling, but we're basically forcing the agent to learn coordinate inverse kinematics. The reward function is kind of minimal. So how do we shape this in general? Even though it's doing basically exactly what we wanted to do, right? We said move forward at some velocity, be energy efficient, and it's basically exploited a similar dynamics here, this like tiny little steps with A1, or with the humanoid, we get some extraneous arm pumping. So how do we try and improve this? So basically, we've seen that training control policies with deep reinforcement learning results kind of in with this task minimalist reward function, we get some unnatural gains. So your reward function was to penalize certain base velocities, so forward lateral or try and track some desired velocity commands. We have some forward lateral and desired yaw rate we'd like the system to move at. To penalize other base velocities, we don't want like vertical oscillations or roll and pitch rates, and we penalize energy. So how can we try and improve this, get a more natural gait? Maybe we can try and add some reward terms, maybe try some base height, or the system move at some height, maybe reward foot air time, so it takes larger steps. So here it's still not quite optimal. One of the feet is still dragging. Maybe if we train again with a different random seed, a different foot will drag. So we can get a better, more natural gait. So here this looks a lot better. We've tuned this a lot. Now the reward function has many particular terms with like very specific weights, right? So to do a grad student descent to try and get this. But really we still don't know what has been learned or how do we interpret this policy, like when will it fail? Basically, you don't have any guarantees on this, even though it does work well in practice. But we also don't know how should we weight and shape reward functions for this for other tasks, right? This was a very complex reward function. Now for a new task, we need to retune all these weights, maybe add some more terms. We can't specify things like a desired foot ground clearance. So here we had some reward on foot swing time. So it's basically how much is the foot coming up off the ground. Flat terrain, this is not energy efficient. On rough terrain, maybe we needed more. We cannot specify this. And then preview of later part of the talk is can we draw any connections to biological systems with this kind of. So actually, normally when we train control policies, we design some control policy by hand. We don't work directly from sensory space directly to like the lowest level of command anyway, right? So we're doing the optimization, we were training more, we were looking more in task space, where are the skates, not where are each of the joints. Also when we reasoned about the kinematics earlier. So what if we just change our action space? So instead of outputting motor positions and torques, we can output some desired foot position or skate position for each of the limbs. So just this simple task change improves a lot. So now we get a lot more nice skating motions with RoboSimian, right? It's a lot closer to what we had done by hand with optimization. We can even train on some simplified task-based systems. So here we've extracted the limbs. So we just have some floating base. We don't see the connection with each of the skates. And here we can train something here, and then transfer to the full system for some added speed up. If we track now with Cartesian PD control, we get some nice emergent bounding gates that we see. So basically the agents learning kind of implicit force control with the environment. Here it has a 10 kilogram mass on top of the robot. It's called kilogram robot. So this is almost 100% of the mass. It can still do a nice bounding gate. I can even accomplish running over some various terrains. This is all with the same kind of simplified reward function. So here the training was in Mujoko or PyBullet, and here's a sim-to-sim transfer. So we had it running at 4 meters per second in this other simulator where this is kind of real time and closely to what we think the hardware should look like. So we tried this afterwards directly on the system. It didn't work. So it was, robot was shaking a lot. The motor dynamics are not being simulated right correctly. So of course there's some sim-to-real mismatch. So we did have to add some things to get the pulse to work on the hardware. So we added some other reward function terms. So basically trying to keep the base steady, some small reward for having the feet swing up high enough, energy penalty of course. And we want to move forward here, so we have some little lateral drift penalty. And also dynamic randomization is very important, right? So we randomize things like the mass of each of the limbs on the robot. Also inertia, added mass to the robot. So maybe we want to see if the robot can handle a different load. So we added up to 5 kilograms through the training process. Also, we randomized where the center of mass is on the robot, and then varied the coefficient of friction with the terrain. So we can basically learn to run over different types of terrain. So with these additions, now we can run over different terrains. So here we have over concrete, grass, different dirts, and basically we think this works well because agents basically learn to adapt with this Cartesian PD control. Basically, learn this implicit force control with the environment. Now we also tested adding increasing loads onto the robot. So here the robot's still bounding with 5 kilograms, so it's almost half of the robot's mass, and it can still bound. So it's a nice result. So now, since we talked about optimization and deep learning, next question is, okay, how do we combine both of these areas? So especially maybe for many systems, we might have access to different control methods. So maybe we have some policy we've trained with reinforcement learning. Maybe we also have some MPC that we've developed. And so one idea is to use the optimization to basically help improve the learning. So right, with the MPC, we have some cost function, how well we expect the system to do. With reinforcement learning, usually we have some value function of what is our expected return from some given state. And so based on these, basically, we can switch based on some horizon, how much reward we expect, what is the value of some state between each of these policies. Basically, now the MPC is kind of a fail-safe method where if we sample something bad with RL, we think we'll get that reward. We can kind of go back to the MPC. MPC, of course, is not going to have as good performance in all areas since we don't know what the coefficient of friction is with the terrain. So ideally, we want to be a bit more robust. So maybe RL can help with drifting to each of these goals. Just to kind of see, okay, what can we say about the RL policy if we sample that action? Conversely, we can also try and use learning to improve trajectory optimization. So here we have some optimization where we want the robot to jump onto some platform, and feet for execution in ideal conditions works well. But now if we put some block underneath the front feet, of course we overpitch, the robot can't jump onto the box anymore. So how can we use this, what we already do know about the system, with optimization and improve this with deep learning? So is this jumping task robust? So here we have the MIT Cheetah 3 jumping onto this platform. Here we have very good knowledge of the whole system. There's markers on the ground where the foot should be before the jump. We have the full dynamics of the system, right? We know exactly where it should land. But now if we just have some small block underneath the front limbs, we tried the same trajectory, right? It didn't pitch correctly, and so it didn't get onto the terrain. So how do we improve this? So this baseline jumping, we have some nonlinear track optimization to generate the jumping motion to get onto the platform. Now we have some feed-forward controller just based on the output joint torques, joint positions, velocities, torques, and also the desired foot positions, which we just apply this feed forward to the robot. However, if we have some block underneath the front feet, right, we overpitch, this doesn't work anymore. So how can we try and improve the jumping with learning? So here, jumping involves very specific joint trajectories. So right, we have an all-foot contact phase, we rear onto the rear legs, which is the rear foot contact phase, and we have a flight phase where we can't control too much. And this is a very specific kind of trajectory, which is difficult to learn from scratch. Right? How do you write down a reward function to say, okay, at this point, the robot should be in the air, right? This is not obvious to do. Maybe we can do some imitation learning. We already have some jumping trajectory that we have in implementation as like a warm start for the learning. Maybe we can learn on top of that or continue learning afterwards. But we already have an approximate solution in the ideal case, right? So maybe we can learn to modify our existing trajectories for robustness. That's some residual learning on top of what we've optimized. So in our controller diagram, this will look like this. We want to augment the optimization with deep reinforcement learning. So R will basically continuously take the current state, the desired end state, and then learn to modify these foot positions that are then augmented to what we already have from the optimization. So we're continuously, as our feedback controller, we go from RL, we're adding enough desired foot offsets onto what we already have from the jumping trajectory. So here now during offline at the beginning, we'll optimize for different jumping trajectories of different distances and heights, and then learn the feedback controller over various different terrains. We have randomness environment, different heights and masses, inertias, ground uncertainties like blocks underneath the front feet, and also different frictions. So right here, here's some two examples. We have a block underneath the rear feet. We're not able to jump into the platform. Now by augmenting our optimization with deep reinforcement learning, and now we can successfully jump to the platform. We also have some target results, the same thing, where the base stretch optimization didn't work. Now we have some uncertainty underneath the front feet. Now we can jump onto the platform. So the last part of the talk, I want to talk about what we've been working on recently trying to get as close as we can to animals, right? So there's no robot that is kind of as agile and nice as what we know from nature. And also, we don't know exactly how this locomotion is produced. So basically, in mammals and vertebrates, we have these spinal cord dynamics. So basically, these neural circuits, spinal cords of mammals, and other vertebrates that can produce locomotion in the absence of descending drive from the brain. Basically, there's the internal circuits that we know from these experiments with decerebrated cats that basically made a transaction here, and the cat could still walk. But we don't know exactly how this is still modulated, right? So there's some ideas that the brain is controlling everything and really sending a lot of drive up to the spinal cord to produce this locomotion. And then there's other schools of thought that are, okay, maybe it's more reflexes through the musculoskeletal system that are producing this kind of locomotion and modulating this. So traditionally, CPGs for quadruped locomotion will have some network of dynamical systems. Here we have some amplitude-controlled phase oscillators. We have one of these for each of the limbs. And so here are the equations, the amplitudes and phases. So we have some amplitude set point we're trying to converge to. So this would be like to speed up. We don't want to take a huge step at first. So basically take a smaller step at the beginning and then converge to some set point. And then we have some phase dynamics for each of the oscillators as well. Where here we can set some frequency. So typically we'll have a different frequency for stance when we're in contact with the ground. And then in the air, so it's like a faster swing as we get to our next contact. Here we'll have some coupling between different oscillators. This will set the gate. So right, if we have these like front left and hind right should be in phase, this would be more of a trot gate. We can also train for other things. This is a trot gate. This is pace. We have symmetry across the left and right sides. We can also do a walk gate. So this is what we showed earlier with 1 foot at a time steering off the ground. So this is one oscillator for each limb. Now we just plan to map these to joint commands. So here we have 3 joints in each of the limbs. So we're mapping these to desired foot positions. We have some trajectory here that each of the feet should follow. And then basically we're mapping these back with inverse kinematics to each of the joints. So this works pretty well, but it requires careful parameter tuning, right? So what should each of these parameters be? What should the set points be? So it should either be maybe optimization based with the genetic algorithm or hand tuned. So I just hand tune these three other gates here. Also, this results in a single fixed gate. So maybe you want to move at different velocities with different styles, maybe different heights. You need to retune this for every desired gate and speed. Also, it's difficult to specify omnidirectional motion now. So maybe we can add some different control on top of this, like virtual model control, by reasoning what should the forces be when we're in contact to turn. Maybe we need to add more states, do adduction and abduction to turn. So we want to see, can we improve the general capabilities of these CPGs or these dynamical systems for robot control with deep reinforcement. So this is what we call CPGRL. So we're trying to learn the central pattern generator instead of hand tuning it before. So our policy is our neural network, which is now going to output these amplitude set points, frequencies, and then we've added some more states. So now basically the RL network is in charge of coordinating the locomotion in between each of the oscillators instead of having it be fixed. So at each control step, the policy is going to output a new set point and a new frequency for each of the links. So it's basically managing the coordination for us. And then we still have the same mapping to desired foot positions, which then we're tracking with inverse kinematics and joint PD control. And then the state estimation is pretty standard. So we're taking IMU data, different joint angles and velocities, torques, whatever we have, sensing foot contact booleans from the robot, and we're plugging this in as input to the policy. So it's aware of the state of the robot. Also, it's aware of the internal states of the CPG. So, but what is the state of our dynamical systems? We have all the amplitudes and phases. And so here it's able to basically know what is the state of my full system. So this one is not noisy, right? We know exactly what the state is of a dynamical system versus the state estimation is still going to be very noisy with all the integration we need to do to figure out what are the linear velocities of the base, for example, since they're noisy. And then we also have as input to the policy desired commands. We want the robot to move at some forward lateral velocity, maybe also turn. So with this, we have some nice properties, such as in being able to on the fly change the body height and swim foot height. So typically this would be difficult to encode the word function. Like we want a command to say, okay, the robot should be at this height. The ground clearance for the swing foot should be this height. So here we can just resample online. What should this height and ground clearance be without really specifying this in the deep reinforcement learning framework. So this is kind of a nice thing that emerges from the framework. So here I've just modulated as we get closer to the tunnel. I just say, okay, the height should be this. The robot goes under the tunnel, comes back up on the other side. And then here I'm just on the fly changing what should this ground clearance be, just in the pattern formation layer. We can also try and answer some questions like what kind of sensory information do we really need? Like what is really needed to coordinate locomotion? How should the robot actually move? And so traditionally in CPGs, this kind of coordination is based on this kind of force feedback idea. So here we would have the phase dynamics, we have the set frequency, like nominal frequency, we have the coupling with other terms, and then we have some force term where is my limb loaded or not? So the idea is if I'm loaded into the ground, I have some strong normal force here. I'm in stance phase, I shouldn't try and pick up this foot off the ground or else it will basically fall. Likewise, if I'm in swing phase and I get an early contact, I shouldn't still try and push this foot into the ground, right? So basically it's trying to slow down or speed up the phase based on environmental interactions. We wanted to see, okay, is this enough to coordinate locomotion? So we removed all the sensory information being input to the policy network except foot contact booleans. And so this is a pretty surprising result actually that this worked real. So we didn't have any noise randomization through the training, which usually we need quite a lot of this to bridge the spectrum gap. So the only feedback that the robot has from the environment is are each of my feet in contact with the ground. And this is still enough to get the robot to walk. So it's not as smooth as before, but it's still not falling enough, right? It's moving forward. Also, we were very interested, do we really need things like motor angles and velocities as input to the system, or is this maybe more of a lower level circuit, so maybe the spinal cord or brain is more sending some high level signals, and there's lower level circuits in the limbs that are taking care of actual muscle dynamics. So here we trained 2 sets of policies. On the left, we have all sensory information that we had before. Here we have some random robustness tests, and on the right, we don't have any joint information. So here the policy doesn't directly observe what are the angles or velocities or torques of each of the limbs, and it's actually, we don't really see any difference in the performance here. So A1, the robot here is 12 kilograms, and we were able to put 13.75 kilograms on it. So this is all the mass we had at the time. So it's over 100% of the nominal mass of the robot. So basically, we don't see too many differences. We also were looking at omnidirectional locomotion. So here's some example tests of turning around in place or moving laterally with both observation space. Here we think probably the joints are more important when turning laterally, so hip adduction and abduction are important. We also trained and tested on this other robot, so it's slightly different. This is an Unitreat Go 1. Also, this is working well. It can still turn laterally and turn about some desired yaw rates. And so now we wanted to see, okay, how many robots can we control with this same policy? So all these policies, all these robots are running the exact same control policy. We don't have any difference. So these robots are very diverse. They have different number of joints. They have different masses, right? So it's actually impressive that the same control policy can actually control all of the robots. So these are ranging from 2 to 100 kilograms. Nominal height is like 0.2 meters to 1 meter. Some of these have different morphologies, right? So like, for example, HiQ has inverted rear knees, or front and rear limbs, versus the robots we were showing before have the same kind of knee configurations. And this big robot has 3 joints, an extra joint each of the limbs. So with this same kind of framework, we can control many robots. Also, we're looking at adding vision in the loop. So how now on top of what we were looking at before with the proprioceptive sensing, we also have vision in the loop. So for example, for a navigation task, also for different gap crossing behaviors. And here we're looking at what sets the gait transition for the animal. So here we see at the beginning, the robot is trotting. So we have diagonal limbs moving. And then based on this basically environment feedback, it has to transition to more of a prong or a jumping gait to get over. And we didn't script this. This kind of emerges naturally through this bioinspired framework that we have. Yeah, it seems to work well for Seminari. Also, all this was being trained offline. So now we're also looking at, okay, how much can we optimize for directly online? So here we're inspired a bit by frogs. So they have these really nice abilities to like turn and jump. It's super nice. And so here we're trying to see, can we optimize similar behaviors online? So of course, the morphologies, it's a bit different. But here we're trying to see, okay, can we have some kind of somewhat close robustness over different terrains? So here we're using Bayesian optimization, trying to optimize these foot force profiles in order to produce these kind of jumping behaviors and see how robust it is with different control methods. Some ongoing work, I'm also looking at human-robot interaction, so trying to adapt to human preferences with this kind of feedback from the robot. Which of these handshakes does the human prefer? Trying to optimize for basically dynamical systems parameters. And here on the right, we're looking at quadruped catching and throwing. So walking around is not super useful for the quadrupeds, so it can actually interact with the environment and do something more involved. So here we're looking at throwing, and the next part will be catching with the robot. Yeah, so for future research, so basically we're still very far from the dynamic abilities of animals, right? This dog is planning, executing control at a super high level where robots are really not so near, I think. So I think that right, this athletic performance and intelligence area is super interesting. And this intersection of machine learning, optimal control, and bioinspired control, I think is an interesting direction towards trying to achieve these same kind of dynamic gates. I'm interested in very diverse systems like robots, vehicles, manipulators, and swing robots now recently in the lab. Also, I think very important is policy interpretability and robustness guarantees. So here basically with the CPG in the loop, instead of just outputting directly joint commands like end-to-end, what most like pure computer scientists are doing, we have this network of dynamical systems, right? So we basically know what the state is at all times. So this is some extracted CPG states from this run. So we basically see exactly how it's modulating each of the feet. We basically know what the phase is at all times. So here we see it's not exactly a trot gate, but we see how it's being modulated. We can kind of forecast, see what should our future states be, and maybe we can add some constraints in the artificial neural network, or even maybe remove many of the layers. So some ongoing work is looking at how many neurons do we really need to express this kind of liquid motion. And then last direction I'm looking at now is neuroscience by robotics. So now we have some muscle models on the loop. So maybe we know something about our system dynamics. Of course, these are simulated. We know some neuronal connectivity in certain animals, and not really for quadrupeds, but for like zebrafish larvae, for example. We have the connectome. Maybe we can use machine learning to try and enforce which connections we do know, and then learn those that we don't. And then, of course, using this to design more optimal robots. So here we see the emergence of different gates. Also, these are quite robust with these muscle models, and have some implicit force control to reject disturbances. I'd like to briefly mention the EPFL Legged Robots course that I've been teaching the last 3 years. So these are 3 of the projects from the class. So first, we are trying to control real systems. So here, for example, we have the Boston Dynamics Atlas. We plan biped locomotion based on divergent motion. Projects 2 and 3 are with quadrupeds. So we're doing quadruped locomotion with simple time generators, live motion. And the students are training their own controllers to try and basically maximize their performance in simulation. I'd like to acknowledge my collaborators. Of course, I couldn't do all this by myself. So these are PIs I work with, PhD students that helped, and also master students that I'm currently supervising. Yeah, thanks a lot for your attention. Happy to take questions.